Hello everyone, this is Ashwini from Cheenta.com. In this video, we will continue with our adventure in geometric transformation. Geometric transformations are extremely important for Mathematical Olympiads, ISI-CMI entrance, but most importantly, they open a new way of thinking about geometry, and I find it very beautiful. In this episode, we will talk about a very nice problem from translation. So what is translation? Translation is simply parallel shift. So you have an object. Let's talk about two-dimensional planes only. You have an object, maybe this square, and you move it. You sort of push it in a particular direction through a particular distance. So maybe you move it horizontally by 3 units to the right. Then the new position of this box or the square is here, and we say that the square experienced a translation or parallel shift. So to describe translation, you need something called a vector. The idea of vector is very interesting in mathematics. You may think about arrows as vectors. Some people do that. Some people represent vectors by coordinates. 2 by 3 is also a vector for these people. And then there are some people who extend the idea of vector, and then they say, okay, the function x squared plus 2x plus 1 is also a vector. This last little part is kind of interesting, and maybe in some session on vector algebra, I'll talk about it. But let's clearly understand why a coordinate is a vector and what is the true meaning of the word vector. So, vector is something which has both direction and magnitude. I hope you have seen this in the physics class or in some mathematics class. So, if I mention 2, 3, that particular point also has a direction starting at the origin and has some magnitude. So if I draw this in the coordinate plane, we have 1, 2, 1, 2, 3. So here it is 2, 3. We can think of the point 2, 3 as all the information that it encapsulates, and that is this arrow starting at the origin and ending at 2, 3, and this arrow has a direction, it's pointing in a particular direction. It also has a magnitude. So the point 2, 3 secretly encapsulates the idea of a particular direction and the idea of particular magnitude. Therefore, 2, 3 can be used to represent a vector. In fact, therefore 2, 3 can be used to represent a translation. Translation means you move an object in the direction of 2, 3 and you move it, the magnitude of movement is this much. So let's suppose we have an object here, and I say that give it a translation 2, 3, what you would do is you would move right by 2 units, up by 3 units, and you basically drag this object from here to here. So this arrow is represented by 2, 3, though it is starting at a very different point where the actual square is. So if I say give the arrow or give the square a translation of 2, 3, then that's exactly what you do. You move it along this particular arrow, which can be broken down into two components: horizontal 2 units, vertical 3 units. Okay, so I hope you understand how we can use vectors to represent translation. Now let's do a very interesting problem using translation. And this is where you can see the true beauty of this particular concept. Here is the problem, and I have talked about this many times in the Math Olympiad program at Cheenta. If you are a member of the Math Olympiad program at Cheenta, you may have seen this before. But anyway, let me tell you what it is. So suppose we have a particular person A, and there is another person B, and this person wants to come from his home, which is this black dot, to his friend's home. But there is a river in between. Maybe I can thin out the river a little bit. Yeah. There is a river in between. So he needs to build a bridge on the river. And the bridge can be only drawn vertically, that is perpendicular to the river. So it can only be drawn vertically. Of course, it can be drawn here or here or here or whatever. So where should this person build the bridge so that the distance traveled by the person is minimum? So for example, the person could build the bridge here, then A to this point. Of course, he will come directly, and let's call this M and this is N, and then he will come from N to B. So of course, this pink distance has some number. You can measure it. But if you build the bridge maybe here, then you can come from A to P. Let's call this point P, Q, and then from Q to B. So this is another option. So we have A, M, N, B as one option, and A, P, Q, B as another option. There are two options. Which one should we opt for? And there are many, many more options that we can do by building the bridge in other positions. Question is, where should we build the bridge to minimize the distance from A to B? And to do that, what we will do is we will use translation. So let me show you how we can do it. Wherever the position of the bridge is, whether it's here, here, or here, doesn't matter. What you can do is you can always translate it to A. So the tip of this bridge to A like this. Okay. So let's do that. Let's translate the bridge to A and put it here. Remember, the width of the bridge, wherever it is actually the same because it's equal to the width of the river. So when you translate it to the point A, it will look like this. Well, of course, you're doing this in your imagination. Now, let's do a very simple thing. Okay, here is the point B, in case we forget. So what we can do is we can actually join this point with B. Here we go. All right. So this is my point P, this is Q, and this is R, suppose. What I want to do is that I want to create a path which is equal to this PB, the length of PB, plus the bridge length. The bridge length is, of course, always constant, so you don't worry about that. But whatever the remaining portion of the path is, after we deduct the bridge length, I want it to be equal to PB. And that would make it the shortest. I'll show you in a minute why. So we will use a very simple trick. We draw the bridge here, wherever the line PB is intersecting the other side of the river, and join this. So this is M, suppose. Of course, MR is equal to AP and MR is parallel to AP. So this is a parallelogram. So AM is equal to PR, and of course RB is RB. So the path AMRB is equal to the bridge, the length of the bridge, which is MR, plus PB. PB is the straight line, right? Because AM is equal to PR, and of course you can add RB to it, right? So AMRB is equal to the bridge plus the length of PB. This is the most important point. And this will actually help us to show that this is the shortest path. Suppose we draw any other path. Let's say this one. Let's call it ST and join TB. How can we show that ASTB is actually a longer path? Well, it's quite simple. What we do is we join PT. Notice that AS is equal to PT, right? AS is equal to PT. AS is equal to PT. And TB is equal to TB, of course. So PT plus TB is equal to AS plus TB, right? But PT plus TB is definitely larger than PB, isn't it? PT plus TB is definitely larger than PB because of the triangular inequality. And that's it. We are done. We have proved that another path will be larger than AMRB, which is equal to the bridge plus PB. See how beautifully the idea of translation can be used to solve this particular problem. Translation can be used to solve many other exciting problems. We discuss these often in the Advanced Math Olympiad programs at Cheenta. And if you are a member of it, you've seen it many times before. Thank you for joining in today. You can check the link in the description for the exciting programs on mathematics, physics, and computer science that we have. I hope you will enjoy it, and I'll see you in the next one. Take care. Bye.